In this video, I'm going to show you about the third part of Lab 3. The third part of Lab 3 is asking you to observe phase lock loop and measure the lock-in range and the capture range of phase lock loop. Phase lock loop, in fact, is to detect the input signal and then use a feedback loop to generate an output signal that is oscillating at the same frequency as the input signal. Here is the circuit we are going to use for phase lock loop. We also use 565 for phase lock loop. From this circuit, you can see the difference of this one from the previous one is that it has the input signal. The input signal is applied at pin 2 through a 100N capacitor. And also note that at pin 2 and pin 3, there's a 1K resistor connected to ground. And also we connect pin 4 and pin 5. As we know, pin 4 is the output of the VCO and pin 5 is the input of the phase detector. So that means after the VCO generates the output signal, we send it back to phase detector so that it can compare the output signal to the input signal to make the output signal oscillating at the same frequency of the input signal. The other connection at pin 7, pin 8, pin 9, pin 10 are the same as previous one. Okay, now let's look at the circuit. Here is our circuit. You can see at pin 2 and pin 3, there's a resistor, 1K resistor connected to ground. And also, we applied input signal through a capacitor at pin 2. And also, we connect pin 5 and pin 4. Pin 4 is our output, so we connect it with oscilloscope. The other connection is exactly the same as the previous one. Then let's look at what the waveform should be. Okay, now you can see the yellow one, the upper one, is our input signal. The blue one, the bottom one, is our output signal. Now, both the input signal and the output signal, their frequency is at 91 kHz. So that means the input signal has been locked by the output signal. They are now in the lock-in range. Now I'm going to increase the input signal. So when you increase the signal, fine-tune it. Do it a little bit by little. So now you can see if you increase the input signal, the output signal will also increase. So now I increase it to 103 kHz. The output signal is still the same as the input signal. So that means it has been locked. It's still in the lock-in range. I'm going to increase a little bit. still in the locking range. A little bit. So now you can see the output signal is not at the same frequency as the input signal. That means it lose lock. It has been unlocked. So when I want the output signal to be the same frequency as the input signal, I'm going to decrease it. Now it's 105 kilohertz. Still, I didn't lock the input signal. Decrease a little bit. Now it's 105 kilohertz. Now you can see the output signal is at the same frequency of the input signal. It gets locked again. So now we are going to measure the locking range. Locking range means first you get locked. Your output signal is at the same frequency of your input signal. Then you change the input signal, either increase or decrease, to know what is the upper limit and the lower limit of your locking range. So first, it gets locked. Then I increase the input signal. You can see the output signal also increased. So when you do this, do it little by little. So it's 109 kilohertz. It is 110 kilohertz. Still in the locking range, but this is almost our upper limit of locking range. Change a little bit. $111, a little bit. Now you can see it get unlocked. It lose lock. So that means our upper limit for locking range is about 110 kilohertz. In fact, since my timing resistor is about 3.86 kilo ohm and my timing capacitor is about 1 ohm, from that formula, I calculate about the free running frequency is at about 70 kilohertz. So that is almost the same as what we observed from the oscilloscope. And based on the locking range equal to 8 times free running frequency divided by the total voltage applied to 565. That is 8 times 70k divided by 12. So that is about 47 kilohertz. So by theory, the upper limit for locking range should be 70 kHz plus 47 kHz, that is 117 kHz. So from what I measured from the oscilloscope, the upper limit for the locking range, in this case about 110 kHz. So that is pretty close. Now let's look at what is the capture range. Capture range means at first you haven't got locked, and then you try to lock the input signal. So now you can see I'm going to decrease the input signal. So now you see the input signal now is 110 kHz, but still the output signal cannot lock the input signal. The output signal's frequency is not as the same as the input signal. I'm going to decrease a little bit. So now it got locked. The output signal's frequency is at the same of the input signal. So now from this case you can see our locking range, the upper limit is about 110 kHz. So when I first got locked, and when we change the input signal to 110 kHz, it still can get locked. But for capture range, it is much smaller. When we decrease the input signal to 108 kHz, the output signal cannot lock the input signal. Until we decrease the input signal to 104 kHz, then the output signal can lock the input signal. So that means the upper limit for capture range is 104 kHz. So now you can see the difference. The upper limit for locking range is about 110 kHz, but the upper limit for capture range is about 104 kHz. So the capture range is smaller than the locking range.